Like this, it works. Welcome back to NE 630, nuclear reactor theory. Last time, we just discussed the derivation of the neutron flux and neutron currents in the XYZ planes, and we showed that the neutron current is given by the total current at the origin is just given by d, negative d, gradient of the flux at the origin, where d is nothing more than 1/3 sigma scattering. So do you know what's the difference between those three terminologies, I, phi, and j? All of those are number of neutrons per centimeter square per second. But what's the difference? Okay, for I, it's a uniform beam, and usually you have monoenergetic neutrons. So this is NV is equal to I, and it is neutron per centimeter square per second. So, and this is beam. This is flux. This is current. What about current? So this is area equal to 1 centimeter square. Area equal to 1 centimeter square. So it is exactly the same, but with the difference of you have neutrons coming and crossing the area, which is the total number of neutrons crossing the area in all direction. So this is what? Scalar. So what about this? So this will be only neutron that goes in only certain direction. So this is also, the area is equal to 1 centimeter square, and this is vector. And in order to get the current from the flux, so if you have a flux like this and you have a preferred direction like this, let's say in direction omega as unit angle, solid angle. So if you want to get the flux is nothing more than J dotted with omega. Okay, guys? So those are the primary definition. You have to understand in reactor physics very well what's the difference between the three things here. So usually we can write the current as equal to negative d grad phi. And current is vector. The gradient operator is vector of a flux. So a vector of a flux, a scalar flux, is a vector, and this is a scalar quantity. And this is very important formula. Usually we call it Fick's law, because it describes a diffusion phenomenon. A diffusion process. So it's like, can somebody give me an example from mechanical engineering, diffusion process? Yeah, gas diffusion. So the C dot is equal to some diffusion coefficient gradient. Let's say this is, we call it M dot gradient C, where C is the concentration here. So, and also like what? Q dot equal to negative K grad T. So this is what? Heat transfer, Fourier law. And the heat flux is equal to negative K multiplied by gradient of T. So whenever you have a change or a gradient, so if you have T high here and T low here, so the change is going from the higher to the lower, but the gradient is going from the lower to the higher. So the gradient will be in this direction. So grad T is from the smaller temperature or lower temperature to the higher temperature, but the heat will be transferred from the hotter surface to the cooler surface. So let's call this T cold. So the heat will go in this direction, in the opposite. So this is why we have the negative sign. And usually Q dot will be equal to some heat diffusivity, and this is what we call the heat diffusion, which is the same like mass diffusion or the neutron diffusion and so on. So it's similar phenomena, and it will be opposite to the direction of the gradient. So if you have the gradient this way, the heat flow will go this way. Again, the diffusion coefficient that we just stated for the neutron diffusion, for neutron diffusions, D is equal to 1 over 3 sigma scattering, as we just described here and in the last lecture. But there is lots of assumption, and in order to do the right thing, you have to do transport analysis for the neutron transport. So the right diffusion coefficient from the transport equation is just 3 sigma total minus mu naught average multiplied by sigma transport, or sigma scattering, sigma scattering. And this is equal to 1 over 3 sigma transport. So sigma transport is the transport cross-section, and it is defined as, the transport cross-section is defined as 3 multiplied by sigma total minus mu naught. What's mu? The cosine theta. So this is the average scattering cosine of the scattering angle. So there is lots of scattering angles when the neutrons will make scattering. So if you average over all mu's, this is the average mu, the average cross-section, the average cosine. And sigma scattering is just the scattering cross-section. So if you do this, you will obtain sigma transport. So this is just the transport cross-section. And usually mu naught, the average of the cosine of the scattering angle to a good approximation is equal to 2/3 the atomic mass number. Atomic mass number. 2/3 the atomic mass number. So now let's start driving the diffusion theory. Neutron diffusion. And this is the heart of the nuclear reactor physics. So usually, if you want to do neutron or reactor physics calculation, if you want to do just fast and easy calculation, you will do the diffusion equation. If you want to do full-blown calculation for reactor physics, 3-dimensional or whatever, usually you do transport or you do Monte Carlo techniques or anything like this. So let's assume that we want to study the diffusion theory. So let's assume that we have a tab here. And there is droplets coming out and you are filling a tank. So there is m dot exit and m dot inlet, and you have total mass m inside. So the time rate of change of the mass inside the tank will be just equal to the mass m dot inlet minus m dot exit. Of course, in case of water, you do not have any destruction for the water molecules or any generation for the water molecules. So this is just what we call continuity equation. So again, same for neutrons, we'll say that the time rate of change of the number of neutrons per time, if I have certain volume like this, and in this volume, if I take a unit volume, this is called controlled volume, and inside the controlled volume, I took a unit volume delta V, then I will apply the continuity theory on, let's say, inside this controlled volume. So the time rate of change of the neutron population here is just coming from two things: all sources minus all things. So what are the sources? What do you think? What are the sources if we have a volume like this and it has neutrons? What are the sources? How can we fit n neutrons inside this source? But let's say, okay, I know that fission is one of them. What else? Radioactive decay. If you put a radiation source, external source inside. So the first thing is external source. So this is external source. And the second one is what? Is fission, as you just said. So what's the fission source? Sigma fission multiplied by phi is total number of fission per second per centimeter cube. If you multiply this by nu, this is the total number of neutrons produced per centimeter cube per second. So nu sigma fission multiplied by phi. Somebody will say, oh, but we have again distribution of neutron energies and a distribution of the cross section has also variation with the energy. But last time, if you remember, we said that we will take average over all the energies inside the nuclear reactor. So what are the sinks? What do you think? Absorption. So there is minus sigma absorption phi, and this is the total number of absorption. What else? Leakage. So minus leakage. And this will be the thing that we will focus on to drive what's the leakage. Again, we will show that the leakage is just the divergence of the current. So let's assume that we have in 3-dimension space, we will have x, y is here, z is here, and you will have a unit or a parallel pipe like this. So this area is what? So this is in the direction of z, so this is delta z, and this is in the direction of x, so this is delta x, and this is in the direction of y, so this is delta y. So you have this area is delta x multiplied by delta y, and so on. So now, last time when I stated that the J plus and J minus are the current in the positive direction and J minus in the minus direction and so on, then we stated that Jx, it was the difference between the positive direction and the negative direction. Do you remember last time we stated that Jx is just equal at 0, was just equal to J plus at 0 minus J minus at 0. So Jx is just the current, the net current that will go in this direction, let's assume. So or net current that will go through this phase, or net current that will go through this phase, or this phase, or whatever, or the other opposite phase here. So the net current means there is current going this way, there is current going this way. The net direction, let's say, we'll assume goes this way. So let's assume the origin is in the center, and then let's assume that this is delta x is half the distance here. So this is delta x, and this is delta x also. This is delta z in this direction, and delta x again here. So if we look at the net current, the difference between the current, let's assume that we are talking about the x direction here. So there is a current here at the top one, let's say net current that goes in and net current that goes out, let's say. So the net contribution from the currents that get from the x direction is just, or the number of neutrons is just Jx at x plus delta x, which what gets in at x plus delta x. Let's say that here is x plus delta x at this surface, and the base at x equals 0, we'll call it x. Or let's assume that the origin is in the center, or just shift this a little bit down, so this would be in the center, and this is Jx at x. So this is the difference between the neutrons that penetrate in the x direction at x plus delta x minus the one that goes at x. So this is just the total number of neutrons per centimeter square per second in the x direction. So in order to get the total number of neutrons, I have to multiply by the area, and the area in this case is just, this is delta y, and this is delta z. So this is delta y, delta z. Again, so this is the net number of neutrons that gets into the volume in the x direction. Again, the net number of neutrons that gets in the y direction is just Jy at y plus delta y minus Jy at y multiplied by the area, but in y direction, here is the y direction. In y direction, the area is delta z, delta x. So delta x, delta z plus, so this is all the neutrons coming from all direction and leaving from all the directions. So this is just to say that this is the difference between m dot inlet and m dot exit, which is the current inlet and current outlet. And the current in this z direction will be at z plus dz minus the current in the z direction at z, and this is multiplied by delta x, delta y. But if you look at here, what's this difference? So if you get dy by dx, it is equal to what? The limit for the delta y divided by delta x, yes? Or df by dx is the limit for df by dx when delta x goes to 0, and this is just equal to the limit when delta x goes to 0 for the function at x plus delta x minus the function at x divided by delta x. And for very small delta x, we can take this out and just leave it like this, f of x plus delta x minus f of x divided by delta x. And this will be roughly, I put roughly here as df by dx. So what's f of x dx minus f of x equal to? It's equal to, from here, this will be equal to the time, the distance rate of a change of the current multiplied by delta x. So we can remove replace can replace this by dj by dx, dgx by dx multiplied by delta x, but we have outside we have delta y and delta z plus dgy by dy. Again, outside we have multiplied by delta y, but outside we have delta x, delta z plus dgz by dz, and we have dz, but we have delta x and delta y from the area. So what's this? This is the volume. So I can take all of this out, and I say that this is dgx by dx plus dj y by dy plus dj z by dz, all multiplied by delta volume. So this one I can write it as what? Divergence of j multiplied by delta v. The divergence operator, the del operator, is just d by dx in the I direction plus d by dy in the j direction plus d by dz in the k direction. And the components for x is what? Jx in the I direction, Jy in the y direction, Jz in the z direction, in the k directions. Then when you make the dot products, this will give you this component here. Yes? If we are talking about unit volume, so we have to divide by what? By delta V. So if we divide by delta V, this will give us divergence J. So in this case, the leakage term is just what? The leakage is defined as the net flux out. The net flux out. So it will be just divergence what? Divergence J. So in this case, I will subtract divergence J here as the new term for the leakage. So now I have an equation that represent the diffusion equation. And the n here, I can write n as what? As the flux divided by what? By the velocity. So now I can rewrite my equation, and this is the equation governing single speed diffusion equation. So this is single speed diffusion equation. One velocity neutron diffusion equation. It's 1 over V dphi by dt equal to external source plus nu sigma efficient phi minus sigma absorption phi minus divergence of J. But we just stated a couple of minutes ago that the current can be represented by a Fick's law. Yes, we just stated that current is nothing more than negative d grad phi just a couple of minutes ago. So if you replace this here, you will obtain 1 over V dphi by dt equal to the source plus nu sigma f phi minus sigma absorption phi minus divergence dot negative by negative is here d grad phi. Okay, guys, what if our system or our volume is uniform? What do we mean by uniform? It has a a uniform distribution of the fuel, for example, or something like this. And D is constant. The diffusion coefficient is constant in the field. So if D is constant, it does not depend on space. D is constant. I can take D out. And in this case, I will get to 1 over V d phi by dt equal to S plus nu sigma fission phi minus sigma absorption phi plus D nabla square phi. And as you see here, this is a linear differential equation of the second order with time dependent. In order to solve this equation, we have to have what? If you have a differential equation, partial differential equation, second order, how many solutions you will have for second order differential equation? 2. Yes? So if this is boundary value problem and initial value problem, you need to know what? You need to know initial values and you need to know boundary condition. So you need to know the boundary condition as well as the initial condition to be able to solve this differential equation. So we have to define some boundary conditions here, an interface condition. So if you have an interface between two at x equals 0 between medium 1 and medium 2, so let's say that this is infinitely long and this is medium 1 and this is medium 2, and let's say that this is the current here J plus in the medium 2 and this is J minus in the medium 2. This is, by the way, this is not square, this is medium 2. And again the same J and J for medium 1 and medium 1. And then we'll have what's get out from medium 1, we will call it air minus, and this is plus, I think. Let me try to look at it. So J minus at 0, the current at 0 here. From last lecture is just 1/4 the flux at 0 plus 1/2 the diffusion coefficient d phi by dx at 0, and J plus is the opposite sign, 1/4 phi at 0 plus d over 2 d phi over by dx at 0. So J plus at 2 at 0, if you want to get J plus at 0 for the medium 2 will be equal to J plus at medium 1 at 0 plus S naught over 2. So if we assume that we have a source here that emit neutrons isotropically, and this is infinite line, so the emission will be only in the x direction, so we expect half the neutrons to go this way and half the neutron to go this way. So half of the source strength is S naught, so half of the source will go in the positive x direction and half will go in the negative x direction. This is why in the positive J2, so this is medium 2, so whatever goes in medium 2, for example, will be whatever goes in the positive direction from whatever come from S1 plus S0 over 2. And J minus 1 in the 0 direction will be half again S0 plus J minus 2 at the 0. So if you apply those two here, you take J minus and J plus and substitute here, for example, you will be able to figure out that when you add and subtract, when you subtract here, those two will let's say will go out, or those two will go out. So you will notice that it will end up phi2 at 0 equal to phi1 at 0. This is very logical. Why? At the interface, the flux is continuous. There's no discontinuity in the flux. So you expect there is interface between the fuel and the moderator. You expect the flux to be continuous between the fuel and the moderator. Yes? If there is two infinite medii and there is a source in between, you expect the flux going between both, because the flux is going in all directions. Expect the flux to be continuous. But the current to be discontinuous. Why? Because the current is in certain direction. So if the neutrons are coming in this direction, and in the other medium, the neutrons are coming in the same direction, there is some contribution from the source. But for the flux itself, no. The flux is continuous at the interface. So this is, if I give you a problem to solve in the homework, and you look for interface between two medii, so the first thing you have to think about is the continuity of the flux at the interface. Okay, guys? So whenever you will take a problem for the homework and you have interface and you want to solve the equation, the first thing for the boundary condition is to think about it is at interface, flux is continuous. So at interface, flux is what? Continuous. And then, again, if you look at if you do the J minus and J plus for you knew that J plus for 2 minus J minus for 2 will give you J for 2. So if you try to subtract, for example, and get the J2 at 0 will be equal to J1 at 0 plus the source term. So if you look at the total current at the interface is discontinuous. Okay, guys? So at the interface, if you look at the flux, this is the flux, continuous function. If you look at the current, this is the current, J. Okay, guys? So this is called interface condition. So what about the boundary condition? So if we have a boundary, and this is the reactor, and this is vacuum. So this is the reactor. So we have a flux, reactor, a flux like this. Do you think at the boundary the flux will go to 0? If you are, let's say, a few centimeters from K-state reactor and you remove the biological shield and the reactor is inside the water, and let's say you get into the tank and you became next to the reactor itself core. Do you think if you're just a centimeter from the reactor core, the flux is 0? No, the flux will continue for some time, then it will decay and drop to 0. So usually to do it mathematically, we will assume that the flux, see, the flux is going like this. So we'll assume that the flux will die out after some extrapolated distance. So you will come here, you will take the tangent at the boundary and extend this linearly. So when you extend this linearly, this is the current going in the positive direction, and this is the current going in the negative direction at x. B means boundary, and this distance we will call it extrapolated distance, and usually we give it a name, lambda ext, extrapolated distance. So the extrapolated distance is defined as it is the distance at which the reactor flux will go to zero outside the reactor. How to get this extrapolated distance? So G plus, excuse me, G plus is the neutron coming out of the reactor. What about G minus?
Backscatter, but shouldn't that be negligible in vacuum?
Yeah, so it's zero. So you do not expect that there is neutrons coming from outside the reactor to get into your reactor. So G minus will be what? G minus at xb is equal to what? 0. And what's J minus from this equation here? Did you see the equation? So it is what? 1/4 the flux at xb plus 1/2 the fusion coefficient d phi by dx at xb. And this is equal to 0. So we can simplify this one and just take this to the other side and then divide d phi by dx divided by phi. So it will be d phi by dx over phi at xb. Both are evaluated at xb, and this is equal to 1/2d. And d, we define d as what? 1/3 sigma transport. So this will be 3/2 sigma transport. 3/2 sigma transport is usually sigma transport. So this is the, let me finish this one first. So what do you think? What's 1/phi d phi by dx? This is what?
Natural law.
Okay. Look at this. Look at this here. What's this? At this point, this is what? Slope. And the slope is equal to what? d phi by dx. Yes? And we define this point to be what? Lambda what? And what's the slope of this line? Just this divided by what? By this. Yes? So this is what? This is the slope. So you can in principle get d phi by dx at this position, at this point, at xb. This is d phi by dx at xb is this distance here. Yes? If you divide d phi by dx at xb, you divide it by lambda extrapolated. This will give you what? The slope. This will give you, and this is phi at 0. This is the flux at 0. So this quantity here, I will go in the other direction so that I can write this quantity here, 1 over phi d phi by dx, all evaluated at xp equal to 3/2 sigma transport. This quantity evaluated at xp is nothing more than 1 over lambda transport. Because lambda transport, again, lambda transport here is phi, which is this, divided by this, phi at 0, or at xb. So 1 over lambda transport will be equal to 3/2 sigma scattering, and lambda transport will be equal to 2/3 1 over sigma transport. So what's 1 over sigma? 1 over the any cross section, 1 over any cross section is the mean free path. So this is what? 2/3 lambda transport. Oh, what I did. Oh, I'm sorry. Forget about it. This is extrapolated, sorry. So this is what? 2/3 lambda transport. I'm sorry. This is extrapolated, not transport. So this is just the extrapolated, the transport mean free path, and this is the extrapolated distance. Extrapolated distance. 2/3 is roughly 0.7. So 0.7 and lambda transport. So the extrapolated distance where the flux will go 0 outside the nuclear reactor will be 0.7 lambda transport. So lambda transport is the transport mean free path. Transport mean free path, if we assume that, let's say it's sigma total minus 3 sigma scattering. So let's assume sigma is in the order of what? Let's assume sigma absorption. If you have near the core you have water or something like this, sigma absorption, let's assume it couple of barn, and sigma scattering. Let's say that this is couple of barn, the sigma. So barn, let's say 10 to the power of minus 24, and the number density is what? 10 to the power of what? 24 multiplied by something here. And let's say that this is even 100 barn or 10 barn or whatever. So this will give you 10, something like 10 centimeters. So 1 over 10 centimeters, yeah, 1/10 of centimeter, yeah, because centimeter minus 1, yeah, 1 over 10. So this is 10 centimeter minus 1, centimeter minus 1. So lambda equal to 1 over sigma. This will be roughly 0.1. This is in what? In meter minus 1. So it will be 0.1 centimeter. So you are talking about 0.7 centimeter, 1 centimeter, or something like this. So you do not say that the neutron flux will go sharply to 0. It will go smoothly until it reaches 0 after a few centimeters, 1 or 2 centimeters. This is why when we talk about power reactors, The core radius is what? 5 meters. What's 1 centimeter with respect to 5 meters? So we can safely say that the neutron flux will go to 0 directly. But this is just mathematical simplicity in order to solve for boundary conditions. So when we try to solve the diffusion equation, if the dimension is very large compared to the diffusion, the transport diffusion, extrapolated distance based on the transport calculation, we will say, okay, we can neglect the transport mean free path with respect to the dimension of the reactor, and we say flux at border is equal to 0. Okay, guys, so when you solve the diffusion equation next couple of lectures, and in the homework, if in the homework we said that, okay, make the assumption that lambda extension is 0, so the flux will be at the boundary equal to 0. If we did not say make this assumption, so you have to say that the flux is flux at x boundary plus lambda extension is equal to 0. It's not at the boundary directly. So just before I finish, what do you think? The diffusion equation is exact, or there is assumption in the derivation? What assumption do you think we did in deriving this equation? So when we see the equation itself, everything was exact up to divergence of J. Yes? But divergence of J in itself, when we calculate J, we make 3 assumptions. To get J equal to grad phi, negative d grad phi, we make assumption. What are the assumptions that we make?
D was constant.
Huh?
You assume D was constant.
What is constant?
D, the diffusion coefficient.
No. In the last lecture, when we calculate J equal to negative d grad phi, we make 3 assumptions to calculate this one.
Isotropic scattering.
Yes, isotropic scattering.
Scattering is more important.
And scattering is more important than absorption. And what else?
Flux is slowly varying.
And flux is slowly varying. So the fusion equation is valid in nuclear reactor calculation, with the exception that you have to have isotropic scattering. If you have a case where you are very near to a control rod, the scattering is not isotropic. So the diffusion equation without transport modification will not be able to solve the control rods. We said that absorption can be neglected with respect to what? Absorption. What about if you are at the interface between fuel and moderator? You are near to the fuel. Absorption cannot be neglected. So what will happen? You have to think about something to do so that you will be able to alter the diffusion equation. This is out of the scope of this course, but usually you modify cross sections and you modify stuff so that the diffusion equation will still valid near to the fuel. What's the third assumption? Flux is slowly varying. The flux near the boundary is not a slowly varying function. We just show that the flux will go to 0 at the extrapolated distance, but technically speaking, the flux will go to 0. Yes? So when you solve the diffusion equation, the transport calculation told us that we have to use this technique so that we make the flux at the boundary a slowly varying function. If we do not make the extrapolated distance, the flux will not be a slowly varying function. So we have to make that the flux has a slowly varying function. Otherwise, if the flux is not a slowly varying function, we will not be able to expand the flux as a Taylor series and omit the higher order term that we did last time. So 3 things you have to make and remember very good when you do calculation and stuff like this. We're using the diffusion equation. The assumption that we assumed last time is valid, but again, if you read more books about reactor physics, you will notice that there is techniques to overcome those limitations. So they do transport calculation and then they amend the diffusion equation with the transport calculation so that the diffusion equation is still valid in present day calculation. Okay guys, so I will stop here and next time we'll start solving the diffusion equation in some medium. Thank you.